lesson, you will calculate experimental probabilities and design simulations and summarize data from your simulations. So theoretical probability, remember, is what should happen in a probability experiment. And we always have a capital P for the probability of the event, whatever that event might be, is the number of times that event would occur out of the total possibilities of that event. So for example, probability of rolling a 2 on a number cube would be 1, because there's only one number 2 on a number cube, out of 6, because there's 6 total possibilities on that number cube. So we would say the probability then is 1/6. Experimental probability is what actually occurs when conducting a probability experiment, or the ratio of relative frequency to the total number of events or trials. So the difference here, you're still going to do a P for probability of an event, but it's going to be the number of times that that event occurs out of the total trials. So it's just one little change here. Here you're actually conducting an experiment, whereas here you're getting the idea theoretically of what should happen. Relative frequency is the number of times an outcome occurred in a probability experiment. So we did a probability experiment, you may remember. We did the bracket challenge. And so every single game had either a win or a loss, one team or another, so that's a flip of a coin. We had a 1 out of 2 for every situation. But we had something else added to that, and that was this idea of what had happened in the past. And we know a number 1 versus a number 16, the number 1 has won 100% of the time. A 2 against a 15, that's 96% of the time that the number 2 won. So we have this weight that's added to the probability. Whereas like an 8-9 seed, the 8 seed has won 47% of the time. This is closer to an actual flip of the coin. Whereas this is not really a flip of a coin because it is 100%. So the probability had a little bit of a weight to it. That's why people who flipped a coin for the whole thing maybe didn't do as well as some people who used skill. Well, that was an experiment, and we found that you had a 1 out of 9 pentillion chance of having every single choice right on that bracket. And it's because of the multiplication of those choices. So we did a rolling dice experiment. We rolled a dice 50 times. And we kept track. Every time I rolled a 1, I marked it, a 2, and so on and so forth. So I have 50 complete rolls in my experiment. So this is 50 total rolls. My denominator is then going to be 50. I want to know the probability of getting at least a 5. So I have a 5 here. There's 6 total 5s. I could get a 7, but no smaller than a 5. I want to get at least a 5. So I could get a 5 or a 6. So that makes 13 total. Try using your ABC key. Can you reduce this? No. So then my probability of rolling at least a 5 is 13 out of 50. Now I know theoretically the probability of rolling at least a 5 would be a 2 out of 6 or a 1/3. The difference here though is we did an actual experiment, so we're getting the number of times we have that outcome over the total number of trials. So you try the example in your notes. A simulation is when you're using an object to act out an event that would be difficult or practical to perform, and a probability model is a mathematical model used to represent the outcomes of an experiment. So here's some things you could use: coins, number cubes, spinners, marbles, discs, cubes. I'm going to show you how you could use your TI-84 for one. So you have to determine each possible outcome and its theoretical probability first, and then find an appropriate probability model for the situation that would represent those outcomes, and define what a trial is for the situation and state the number of trials to be conducted. So when you create an experiment, you have to have these 3 steps considered. For example, if I'm going to do a number cube experiment, I know that I have to roll the number cube. I have to say how many times I'm going to do it, 20 times. I have to keep track of each value as it's rolled, and we know that that would work because you could get a value of 1 out of 6. In this situation, Jacob is inspecting bike frames as they come through the assembly line, and from previous observations, he expects to find a weld defect in 1 out of every 10 frames. So 1 out of 10 is going to have a weld defect, and a design defect in 1 out of every 20. So 1 out of 20 has a design defect. Now, design a simulation using Jacob's expectation of defects and assume that a frame can only have 1 defect. So in this situation, you can come up with some idea of what you would want to use. And what we're going to use is a random number generator. And what that means is I'm going to pick the numbers 0 through 20. So I have 20 total numbers here. And what I'm going to designate is this probability 1 out of 10. So that's going to be 2 numbers. So I'm going to say if I roll a 0 or a 1, or I pick a 0 or 1, that means a weld defect. Because that is 2 numbers out of 20, which would be that 1 out of 10. And then a design defect, I'm going to have be represented by the number 2. So that's going to be design defect. And then if I get any number from 3 all the way up to 20, then that's going to be no defect or none. That means it's good coming off the assembly line. So how we do a random number generator is on your TI-84, what you're going to do is select math. So here's my math key. I'm going to scroll over to PRB, probability, and my random number generator is this number 5. So I'm going to click on the number 5, and then I have to tell what numbers that I want to input. So in this case, I want to do the numbers 0, and I want to go all the way up to 19. If you count that, that's 0 through 19. And I want to do 40 trials. And you can pick as many trials as you want to do, but I think 40 is pretty good. So when I'm done, I will have a total of 40 here. Whatever my numbers are going to be out of 40. So remember, a weld was getting a 0 or 1, design was getting a 2, and this was 3 all the way up to 19. So I have a 0, a 2, a 13, a 19, a 12, a 6, a 1, a 19, a 3, a 7, a 2, a 4, a 17, a 7, an 11, a 12, a 0, a 1, another 0. When I get 5, I need to tally across. I forgot that there. A 13, a 14, a 17, a 7, a 2, a 9, a 19, a 13, a 10, a 12, an 18, a 13, a 15, 11, a 6, a 4, a 12, a 17, a 2, a 9, and another 9. So we should have 40 total if we had our 40 numbers set up here. If you would look to see what is the probability that I would have a weld defect, well, that would be 5 out of 40, which you could reduce to 1/8. A design defect would be 4 out of 40, which you could reduce to 1/10. And then you can count how many have no defect at all, 5, 10, 15, 20, 25, 26, or you can use subtraction if you wanted to from there. 31 out of 40. I don't think that reduces at all. So we found our experimental probability of Jacob's situation with the defects, and we used a random number generator on our TI-84 to do that. Now you can choose other models, spinners, dice, things like that, but know that you have some other, on your Chromebook there's some things you could use, on your TI-84 there's some things you could use to do simulations. So you try the example in your notes.